Hi, today we're going to be working with trig identities. That means that a trig function can be rewritten in another form. The identities mean equals for equals. All of these you have to actually memorize. They're not given to you on the reference card. They're not that hard. For the most part, I'll tell you little things that you actually already know. So cosecant, you know, is sine flipped. So cosecant is literally sine flipped, the reciprocal, and that's why cosecant is the equivalent of 1 over sine. Same thing with secant. Secant is cosine flipped, reciprocate. So secant and 1 over cosine are identical. They mean the same thing. Now cotangent is tangent flipped. Now this one, oops, sorry, my color didn't change. Let me take that off. This one is true. We don't normally use cotangent as 1 over tan a lot. We mostly use the other version of it. So cotangent is equal to 1 over tan, and it's also there also is another way to represent it. But before I talk about that one, I would want to do tangent. Tangent is sine over cosine. So you're like, oh my God, how am I going to remember these? Well, the cosecant is sine flipped is easy. The secant is cosine flipped. That's kind of easy. And then to memorize that tangent is sine over cosine, just go back to SOHCAHTOA. Since tangent is O over A and tangent O goes with sine and A goes with cosine, then it should make sense then that tangent is sine for O over cosine, which is A. That's like your TOA, SOHCAHTOA. And then cotangent, the one I said I'd go back to, is basically that one flipped. So it's A over O, which is why it's cosine over sine. All right, so before I go on to the other identity, I want to practice using these three first. So in example 1, you have to simplify and express the following as a constant. That means a number, or a single function. That means one function. Notice there are two. So basically these are simplify problems. In order to simplify these, you're going to have to replace one or both functions with an equal for it so that we can actually break something down. It sounds a little complicated, and it kind of is. You'll get better with it with experience. So let's do the first problem. So problem number 1, we have to break down cosine theta times cosecant theta. Regular cosine and sine are rock bottom. There is nothing more you can do with that one. So I'm just going to write that. Sine theta and cosine theta, just regular cosine and sine by itself, are rock bottom. Nothing more you can do. So cosine theta is just going to stay cosine theta for a second. Now, cosecant theta, though, is a different story. Cosecant theta, we can replace, and I highlighted in yellow for a reason, cosecant theta up here can be replaced with 1 over sine theta. So all the stuff you learned about simplifying fractions are going to come into play. You now have to multiply these two guys together. And what you're really doing is multiplying fractions. First, you would try to cancel like terms, but we don't have anything that are like. And then after you do that, you multiply side to side. Not cross multiply. That's if it's a proportion. So cosine times 1 on the numerators is cosine theta. 1 times sine in the denominators is sine theta. And then we're getting there, and then cosine theta over sine theta is actually not simplified enough because sine over cosine theta that I'm circling right up there is actually equal to tangent theta. So we can replace that with tangent theta. And I'm going to extend the page. Okay, so that's equal to tan theta. And I broke down the original problem as a single function. So that is the end, and that's what it's equal to. Example number 2, simplify and express in terms of a constant or a single function. All right, basically they want you to simplify. So secant theta. Well, I can do something with secant theta. Secant theta is the green formula up there. So I can replace that with 1 over cosine theta. Again, we are multiplying. When there's no operation, it's multiply. And then we have to do cotangent. Now, cotangent, there are 2 formulas. But you definitely are not going to want to do this one because replacing 1 over tan in place of cotan won't really help us. So this one is probably going to be better because I have a cosine there and already I have a cosine in the existing problem. So I would rather use that one instead. So I'm going to replace cotangent theta with cosine theta over sine theta. All right, well again, I'm multiplying fractions. I can reduce before I multiply. Cosine and cosine cancel out. You're left with 1 in the numerator, and you're left with sine theta in the denominator. And 1 over sine theta is a single function because there is only a sine theta, but 1 over sine theta would be better written as cosecant. And I'm color coding so you can match up. 1 over sine theta is the cosecant guy above. So you want to try to put it in smallest terms as possible. Okay, example 3. Again, simplify and express in terms of a constant, that means a number, or a single function. All right, so I have tangent divided by secant. So tangent is my pink guy above, and secant is my green guy above. All right, so tangent, I'm going to replace that with sine theta over cosine theta. Then I have a fraction bar, which means division. And then I have secant, which is 1 over cosine. So I have this ugly looking thing, but basically it's a fraction, the top fraction, divided by the second fraction. And when we divide 2 fractions, we keep the fraction, we change that to multiply, and then we reciprocate what we're dividing, which is flip. So that really is going to be cosine theta over sine theta, keep, change to multiply, and then reciprocate. Oh, I apologize. I'm sorry, I probably just confused you. Tangent theta is not what I wrote. Tangent theta is sine over cosine. So let's erase that. Sorry about that. So we're going to keep the numerator. We're going to change to multiply, and then we're going to reciprocate the denominator. All right, and then just like the previous 2 problems, when you are multiplying, you can cancel before you multiply. So cosine in the denominator and cosine in the numerator reduce, cancel out, and then you're left with sine in the numerator over 1, which basically you don't need, so the answer is sine theta. Really does take a lot to get used to. It just gets better with practice. All right, now before I flip the page, let me talk about the last identity I didn't get to. The last identity I didn't get to are the Pythagorean identities. This one is extremely important. It gets tested a lot on the regions. Sine squared theta plus cosine squared theta equals 1. And where it comes from is my little diagram above. Remember that x is cosine and y is sine on the unit circle. So if I go to my little picture and highlight, so x is cosine and y is sine on the unit circle, which means the radius is 1. Now that's a right triangle, and if I actually put my ABCs on there, this should make sense. This is A, B, C. So A squared plus B squared equals C squared. And A is sine, and B is cosine, and C is 1. So sine squared plus cosine squared equals 1. It's basically the Pythagorean theorem with sine and cosine representing x and y, and the 1 being the hypotenuse. That's where that identity comes from, and that's going to be, again, tested a lot. These other ones that have arrows drawn to them, that means that those are extensions of that one single identity. For instance, if we were to subtract cosine squared over to the other side, you would get this line right there. All right, so subtracting cosine squared will give you this identity, which is just the yellow one changed up. If instead you kept everything the same, but you subtracted over sine squared instead, you would get this new identity. These other two identities come from the extension of the bigger picture that I do not have drawn. But you can also get these two by another method, which I have in the last example, which I will do. So I'll talk about those two later on. All right, so we're going to now do a couple more problems and keep that identity in mind. All right, so problem number 4, simplify and express in terms of a constant or a single function. Now we have two operations going on in example 4. We have the multiply, so we can distribute, and we also have the subtraction inside. Now the problem can be done either way, and you're not going to know with the little experience you have which way would be the better way to do it. It's just going to come with time. So rather than doing it both ways, I'm just going to tell you that the best way to do this problem would be to actually look at the subtraction, because that comes from the identity we just did. So I'm going to go ahead and write that identity. Recall from the front page that sine squared theta plus cosine squared theta equals 1. If I subtract over cosine squared theta, I get sine squared theta equals 1 minus cosine squared theta. So there it is right there. 1 minus cosine squared, 1 minus cosine squared. I can replace that with sine squared theta. So by doing that substitution first, it does condense it better than doing the distribution step first. So we still have the cosecant. So I can't do anything at this point. That means I'm definitely going to substitute. Cosecant, again, from the first side is sine flipped. So I'm going to replace that with 1 over sine theta. Putting that over 1. And this can reduce. Sine squared theta is kind of like x squared, and sine on the bottom is kind of like x. So this will take away one of the two signs in the numerator. So that reduces to just sine theta. And now we're multiplying. 1 times sine theta in the numerator is sine theta. And in the denominator, everything is 1. So this is your final answer. All right, problem number 2. I'll move that out of the way. Okay, so problem number 2, we have that cosine of 2 theta. Now cosine by itself is rock bottom, but cosine 2 theta is actually our double angle. So we can replace something with that. So 2 theta, you can't just like divide a theta with a theta because it's trapped with the cosine. So you're going to have to now go to your formula card and look at the 3 formulas associated with cosine 2 theta. I'm going to write them over here to the left, but please don't write them and get in the way of the other problem. You can use your formula card. So if you look at your formula card, you're going to see that there are 3 formulas for this. Now, any one of the 3 formulas can be replaced with that yellow cosine 2 theta that I have highlighted, but one would actually be the best. Well, let's talk about which one would be the worst. Because the other guy in the problem is sine squared, you probably don't want to use this formula because that one introduces a second function, and it can be done, but that will probably not be to your advantage to use that one. Both of the other 2 functions have a sine squared in it. So both of the other 2 would probably be better options. Now, of the 2 formulas we have left, which one is the best? Well, again, because I have a single sine squared, and this has a single sine squared in it, this one would probably be the better one, although this one would have worked also. So I'm going to go with formula number 1, and I'm going to use that one instead. All right, so in place of my yellow highlight, I am now going to write that formula in place of it. So that's going to give you cosine squared. Now, the A in the formula is just a generic. Since our problem has a theta, we can just use a theta now, minus sine squared theta. So that's just the yellow part. Now I'm going to get rid of my formula. Okay, and now to finish off the rest of the problem, I still have a minus sine squared theta in the problem, and I still have it over cosine theta. So all I substituted in was the yellow formula. Now simplifying, and I apologize, that's a plus sign. Okay, so now simplifying the problem. I can now add and subtract like terms in the numerator to condense that. That would be my order of operations. Well, negative sine squared and positive sine squared, they're opposite terms, which means they add up to 0. So those will go away. So now you're left with cosine squared theta over cosine theta. All right, so reducing that because I have a cosine squared, which means there's 2 of them. Now, if you really have to write cosine squared as cosine theta times cosine theta over cosine in order to see what to reduce, you can. If you can go ahead and know that cosine goes into cosine squared and you have a cosine left, you can just do it that easily as well too. All right, and the last problem. So I'm going to erase that. All right, the last problem, example 6 says simplify and express again as a constant or a single function. Well, cosine theta is rock bottom. There's no squared, so there's nothing more I can do with that. And sine theta is also rock bottom. All right, so there's nothing more I can do with that as far as substituting. So let's look at cotangent. Cotangent from the front page has 2 formulas, but the one I want would probably be the one that's cosine over sine. So we're going to keep 1 plus cosine theta all over sine theta. And we're going to replace cotangent theta with cosine theta over sine theta. And now we have 2 fractions being subtracted. When you are subtracting fractions, you need an LCD. If you don't have one, then you're going to have to actually create it. But luckily, both our denominators are the same. So we do, in fact, already have common denominators. That's good. So now we can go ahead and combine them. When you combine two fractions by subtraction, you keep the denominator, and then you add or subtract the numerators. Well, 1 plus cosine theta minus cosine theta, the plus cosine and the minus cosine are opposites, and opposites add up to 0. So then you're left with just the 1. And 1 over sine theta is not done enough because we know that sine flipped, and sine flipped is cosecant theta. Okay, lastly, example 7. Starting with sine theta plus cosine squared theta equals 1, derive that other formula that I showed you on the front page. So this was actually a Regents question. It was 2 points, and you had to know how to actually go from that formula to the other formula. Well, it might help to actually know what that other formula looks like if you expanded it or replaced it. So tangent squared is sine squared theta over cosine squared theta. Oh, and you're like, how did I get that? Well, let's go back to the front. And let's talk about squares. All of these formulas, if I square them, I would square everything. So if I were to square cosecant squared, it means I would square this one and that one. So that would be 1 over sine squared. And you don't have to write this. I'm only just telling you what would happen. If you were to square secant squared, you would basically not have to square the 1 because that's going to stay 1. But if you were to square it, you would get 1 over cosine squared. Same thing with cotangent. If you were to square that, you would basically square both pieces. So now that you understand what squaring does, it squares the pieces. That's how I got tangent squared is sine squared over cosine squared plus 1 equals, and then secant squared, well, secant is 1 over cosine, but since I'm squaring it, I have to square the cosine. Now, if you notice that end formula, you have a divide cosine on 2 of them, that's what we're going to do on our starting problem. If we divide out cosine squared theta throughout the entire equation, and you've done stuff like this before. If you have an equation, you can multiply anything you want to everything, you can divide anything you want to everything, or you can add or subtract both sides by the same thing to keep the equation equivalent. That's the same idea. When I divide out cosine squared, sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is itself, so it makes 1 when you divide 2 of the same. And then 1 over cosine squared is secant, so that's going to be secant squared. And we just derived the formula. I know that was a little bit hard, and on the Regents, that was a highly missed question. This is not a normal question. Examples 1 to 6 are the more normal questions. Now I'm going to stop the video. I'm actually going to create another video to do half the homework problems so that you can try them and at least see how to do half of them. If you care to watch that, you can watch that video as well.